The equivalence point is the point where we've added exactly the right number of moles of hydroxide to neutralize all the acetic acid. So what we actually end up with is a weak base, the acetate in water. So this ends up being calculating the pH of a weak base of the acetate. So the first thing we need to figure out is the concentration of the acetate. So assuming all the acetic acid is transferred to acetic acid to acetate, we can say that it's the same number of moles of acetic acid divided by the total volume. Another way to do it is to calculate the moles of base that have been added. Divide that by the total volume, you get the same answer. So if we do it in terms of the acetic acid, we start off with 0.1 molar solution at 50 milliliters, or 0.05 liters. So that's all, the acetic acid, so that's all being converted to acetate. The total volume is the 50 mils we started with, plus the 25 mils of hydroxide that we needed to get to the equivalence point. And so we end up with a concentration of acetate of 0.667 molar. Now what we have is a weak base. So this can now come to equilibrium. So the Kb expression is acetate plus water will reform some acetic acid, will accept a proton, and what you're left with is hydroxide. So we can do our ice table. We know the initial acetate concentration was 0.0667. Before it comes to equilibrium, there's no acetic acid or hydroxide. We're going to lose some acetate, gain some acetic acid and hydroxide. So equilibrium, 0.0667 minus x, x and x. Okay. Now to solve this equation, we need to know the Kb. The Kb we can find, we don't know the Kb, but we do know the Ka for its conjugate base. Remember, conjugate differs by just one proton. So for conjugate acid-base pairs, you can use this equation. Kw, which is 1 times 10 to the minus 14. The Ka for acetic acid is 1.7 times 10 to the minus 5. So that gives us the Kb for acetate, which is 5.71 times 10 to the minus 10. So that's a very small equilibrium. It says that the reaction is mainly over towards the reactants, not the products. So what that means is our value of x is going to be small. So I think we're safe to say that we can ignore this minus x, because it's going to be such a small number that it really won't have an effect. So if we put these equilibrium numbers into our Kb, so just products of reactants. Okay, Kb is going to end up being x squared, products over 0.0667. And we know that that equals 5.71 times 10 to the minus 10. So now we can solve for x. It's going to be 0.0667 times 5.71 times 10 to the minus 10. And we square root the whole thing to find x. And x, and remember in this case, if we look at that ice table, x is the hydroxide concentration. So what we're solving for here is hydroxide. And that ends up being 6.17 times 10 to the minus 6 molar. And we need to get the pH from that. There's a couple of different ways of doing it. One way is to take negative log to give us a pOH. And the pOH is going to be somewhere near 6, 5 point something. It ends up being 5.21. And then we can do 14 minus that. So pH equals 14 minus pOH. And the pH ends up being 8.79.